Okay, so if you weren't here just a minute ago, please be aware that I intend to always, it's always as soon as I start talking, everybody shows up. That's how it goes. All right, so, oh my gosh. Okay. All right, so if you didn't hear me say this before, I'm planning on giving you Tuesday next week off from lab, and I will probably take the points that were originally assigned for that lab and slam them into the oral presentation, which is following. So, and that'll give me time to double check the groups, see who's still in the class, who's left, etc., and do all that crap. So next Tuesday, do not come to lab, do your own thing. I guess, yeah, I'll worry about that. I'll send you an email. Let's just worry about next Tuesday, but assume you're not going to have a normal lab next Tuesday, okay? I'll get that figured out tomorrow when I have time. That said, let's start talking about magnetic forces on charges and wires. We alluded to this a little bit last time with the right-hand rule, and we started doing some simple problems. Okay, and let's screen share. Let's see what we can do here. Let's see. If you're curious, here was the quiz I had lined up for you. And maybe what we could do is do the interesting problem here. And I just want to point out some of the things that you see here and show you how this relates to a problem we're about to do. So this was the lab that we were going to do on Tuesday. We're not going to do it. We'll do something else. Get that out of here. The idea is, let's say you have an electron that's accelerated by a potential difference. Does that sound like chapter 24? I hope it does. You might remember that we could use an energy equation from chapter 24 to figure out the speed of an electron after it accelerates. And then it turns out that accelerating potential difference is going to relate to some various factors with the electric charge and the mass, the magnetic field. And so the idea was we were going to see how electric fields and magnetic fields could be used together. Now, I happen to have a problem in the workbook that's very similar to this. This would be some numbers, and we'll worry about this later. Whoops, wrong button. So let's go to the workbook now and see what happens. Oh, and this was we started out on page 137, right? And we did this problem last time. So now we're getting to here. We kind of talked about this last time. So now I want to talk about problems where there's both an electric field and a magnetic field, because this relates to real life applications, as I was alluding to. Let's start with this 28.3 and use it as a warm-up, okay? So you have a negative ion. It enters a region of space with a uniform external field. Notice I don't say if it's electric or magnetic. Okay, so this shaded region here is the region with external field. And we want it to travel in a circular path. Which of these answers or which of these solutions could it be? Or is it impossible to determine?
I'm going to say impossible.
Take a second to think. We want the ion to travel in that shape. Oh, go ahead, Nick.
I'm just saying because you like to put the none of the above so often. I'm just guessing it's that one.
Exactly. And since I like to put that so often, you would then know it's not that one for this one, because I would try to trick you. So it's not impossible. This can happen. So that said, Nick took his shot. What does somebody else think? We want it to curve.
Magnetic?
Magnetic. So if you didn't see this before, you might remember so this was the correct answer. It turns out magnetic fields are the fields that can make charges move in circles. Going back a few pages, remember we showed that simulation and it was going around in a circle when I set the V perpendicular to 0? So it's possible this would work. So now, what direction should you use for the field? So to be clear, we know the electric field is 0, the magnetic field is non-zero, our charge is moving this way. What direction should the magnetic field point?
Negative K hat.
So let's see. We had a suggestion. Usually I try to do blue. So let's see if this is right. And this is my kind of guess, right? This is how I do it. I take a guess and then I see if it's right. Okay, if that's true, let's think about this. At this point, the velocity is upwards. What direction do I need the force to be?
The X.
This way. So now think, line up the fingers. You could put your hand right up to the screen. Line up your fingers with V, curl them to B, and my finger points to the left. But this is a negative ion, which flips it, and that is correct. Nice job. So that's the direction of the force. Again, line up your fingers with V, curl the fingers to B, and if I could show you on the screen here on the whiteboard. Get me up there. So we had this situation. There's my marker. The velocity's this way. I had a negative charge, and that was the trick here. I was trying to see if you remember that, and you did. Somebody said if the B field is into the page here, so you'll oftentimes hear me say that magnetic field, B field, I'll say it interchangeably. In this case, V goes to B, thumb points this way, because it's negative, flip it. There's the force. V goes to B, negative, flip it. Okay, so that's our warm-up from last time. Let's take a look at the next one now. This one gets pretty interesting. So look at 28.4. Whoa, there's a big one there. All right. So let's look at 28.4. I'm going to get it written up so we can talk about it. And if I'm too slow, remember, you've got the solutions in the workbook too, okay? Ah, this mouse. Sorry, I'm getting tangled up here, all the cables. What number is this? 28.4. We have a positive charge. Moving this way. Okay, and it looks like I drew I hat, J hat, K hat is out. Okay, and what else do we know? Separated by distance d. Oops, that's blue. Has magnitude B. Gravity is negligible. Got it. All right. So we got this situation. Oh, did it say which direction the B field was pointing?
Out of the page.
Out of the page, thanks. Okay, so remember that a dot means out of the page, and so actually I could make this a little bit easier. I could just say B external is B in the K hat. All right. And so what direction is the magnetic force? Let's see here. Let me get my V goes to nope, V goes to nope, V goes to nope, V goes to B, yes, force is down, positive charge, okay. So hopefully that's what you thought. I'll just draw a single line. Is that okay with everybody? I hope so. So the idea, again, I just try out different orientations. Okay, so let's see the next part. Okay, if the magnetic force was the only force present, obviously this thing would deflect downwards. However, we could apply a voltage to the parallel plates and cause an electric force to balance it. Which plate needs to be at higher voltage? Okay, somebody walk me through this now. This is starting to get more and more like the lab that we aren't going to do. But yeah, so if you wanted to...
I've got a
go ahead.
question, and I could be totally wrong, but don't we find we line our fingers up with V and curl it towards F to find the B field?
No.
Is that wrong? Okay, you curl
That's
it towards
wrong.
the B field to find F.
In a cross product, it's always start here, go to there, get that.
Okay, got it.
Got it?
Yeah.
Yep. So you start at the first input, curl to the second input of the cross product. The output of the cross product is the thumb.
Got it.
Good. Okay. So now let's think here. Basically, I want to apply some voltage to these plates. Do I hook up the battery like this, or do I hook it up like that? That's a reasonable question, right? So help me think it through. Any thoughts? Somebody take a shot at it. And you don't necessarily have to know right away. How would you start thinking about it?
I have an idea.
Oh,
So what was that? Sorry.
I was just going to say that if we wanted it to be balanced, so we want force to go up.
Okay, we need a force to go up from the electric field. Otherwise, it won't be balanced. Does everybody agree with that? I hope they do. Good. Okay, so then what were you going to say next when I interrupted you? Sorry.
So maybe the negative. So the top would be negative. No, yes. I forgot what I was thinking.
Oh, you're on the right track. So let's think. Okay, so rather than try and get it right, this is one of those problems where you take a guess, see if it's right, and if your guess is wrong, you fix it. So this is one of those problems. Basically, you're doing trial and error. You said consider if the top is negative, right? Well, wouldn't that make the bottom positive? Is that right? Somebody else. You already took your chance, and I'm going to say, let's make somebody else squirm now, okay? So that was good. Let's think. Somebody else. Is this going to set up, oh, I don't know. What does this make you think of? Two parallel plates. One of them's got plus charges. One of them's got minus charges. What did we do with that back in whatever chapter? You know, the plate separation. Maybe I'm not doing a good job here. I'm thinking about
calculate the electric field.
Yeah, that's what I was trying to. I'm like, when I think of parallel plates and I see D, I think V equals Ed. But so there's an electric field. So Trey, which way is the electric field for this set of parallel plates? That's why we use parallel plates, because it sets up a constant E field, right? Which way is it, Trey?
It would be pointing up.
So there's my electric field if I made the top plate have negative charges. Is that the correct direction to cause that upward force on a positive charge? Yes. Right? And so the other way you could think about it is, shouldn't a plus charge be attracted upwards? You bet. We've still not answered the question, though. The question was, which plate needs to be connected to higher voltage? The positive. So this would be the high voltage plate. And this would be the low voltage plate. And this could be 0 and this could be 10 volts, or this could be 5 volts and this could be negative 5 volts, but whatever, right? Okay. So, all right. Any questions about that? Let's jump back into here. How do I get the potential difference between the plates required? Well, now I hope you could see this. The trick is we want the forces to balance. So we write a force magnitude equation. Be careful here. The force magnitude electric equals the force magnitude of magnetic, right? In this case, this one is going to be QE. This one over here is Q. Now we got to be careful. I need the magnitude of V cross B. All right. So this means take the magnitude of V cross B. When we do this, in this case, hopefully you remember from cross products, the magnitude is V B times sine of some angle. I'll get out of the way. So that's supposed to be the angle between. So it's V times B times sine of the angle between them. Well, what's the angle between V and B?
90.
90, right? So again, just showing you, V is this way, B is that way. Clearly that's a right angle, right? Okay. Oops, I lost a marker somewhere, whatever. Okay. Oh, shoot. My red. Oh, there it is. All right. So in this case, since it's 90, sine of 90 is 1, we're good to go. So in this special case, we get QVB. Nice. All right. Okay. Well, Q drops out. How do I get the electric field related to the voltage? I know the magnitude of the electric field is, remember, V equals ed. That's how I remember it. So E equals V over D, or check the units. Coulombs, what was it? Newtons per coulomb or volts per meter? Volts per meter. There we go. And so from there, I think it's pretty easy. If we know this, it looks like delta V is equal to V D B. Now, just to keep my letter V's straight, you'll probably see me doing this a lot today. Just to keep track of a capital V for voltage versus a lowercase v for speed. You could do that if you want. You could do whatever you want, but you better do something to keep straight voltage and V, speed. They're different, and they appear in a lot of equations at the same time in this chapter. So that's what I recommend. So far, so good? I hope. Let's get back in there. All right. What if you want a negative charge to do this? Think that through.
Flip the electric field.
That's what you'd think, isn't it?
No, you have to put the positive plate at the top. That is what I think.
Yeah, it turns out, of course, that's not right. Isn't that crazy? Let me show you why. If you put a negative charge in there, both forces flip. Look at this. If you put a positive charge, the electric force is up and the magnetic is down. Since they both depend on the charge, they both flip. It turns out this works exactly the same for a negative charge. Isn't that crazy? Okay. I hope that makes some sense there. But think that I'm going to pause here. Another way you could see this is right here. Didn't the charge drop out? Kind of cool, right?
That was my next guess.
So very, very counterintuitive. Yeah, exactly, right? So it's counterintuitive. Magnetism gets very fun. All right, so let's take a look here. Let's see what else we have in here. If it was slower, okay, so let's do this. Let's say this thing is moving slower now. For some reason, let's say you redo the whole problem and you used a smaller V. Is that going to matter? And if so, which way is it deflected? Take a guess. Go for it.
Yes.
Yeah. Okay. So
And then it would be deflected upwards.
Why? What's the reasoning?
Because we base the voltage off the higher velocity. And so any lower velocity wouldn't have enough magnetic force to overcome the electric field force.
Okay, I'll go with that. I was good. Exactly. That's what I was really digging at. The magnetic force depends on velocity. So if you lower the velocity, this force gets too small, the electric force wins and it dominates. That's assuming, like Trey said, you keep the voltages the same. So if you shot a second one with lower velocity, it would go up. What if you go too fast? If you go too fast, which force dominates?
The magnetic force?
So let me get this straight. You just told me you could put a pair of magnets here and make a magnetic field. You could then take two parallel plates and put them in here and apply a voltage. And when you adjust the voltage, only one possible velocity can get through undeflected. It's almost as if you're using this experimental apparatus to select one velocity that gets through. And in fact, what if we put a piece of plastic here with a small hole in it with a marker that doesn't work? Anything that's too fast, ding, ding, or whoops, sorry, too fast, bong, bong. Anything too slow, ding, ding. Anything just right goes right on through. What you can do is you can use this experimental device. This is called a velocity selector. Ooh. And what it does is it selects one particular velocity based on the voltage and the strength of the magnets, and only that particular speed gets through. So looking at this another way, if you rearrange this, the speed that gets through, if we solve this for little v, would be
Almost.
there we go. Oh, yeah, right. So V is equal to the, you could basically relate the voltage to the external field and the distance. And so what this is the start of a mass spectrometer. What? Okay. What were you going to say there?
Yeah, I got a question. And I'm probably way off base here, but basically everything you're explaining kind of makes me think of the particle collider. Is this?
Yes.
This is what they use, the technology sort of idea behind it?
Let's take a look on the next page in the workbook, shall we?
Oh, of course.
All right. So it relates to that. Okay. And so what Nick just asked about was a particle accelerator. So give me just a second. All right. Yeah, ion mass matters. I'm going to this is an important question. I want you guys to try this again later at home, like maybe after you, yeah. So that said, it also relates to this one. This is not required, but it turns out you can actually take a thin piece of metal, and normally you don't do this with a sheet of aluminum foil. A sheet of aluminum foil is way too thick. Aluminum foil is too thick to do this. All right. So what you would do is you would use a small piece of metal that's been evaporated and let it dry out on a piece of semiconductor. And then you get something that's extremely thin, microns thin or less. And the idea is you can actually send current through this. And what will happen is certain charges will get deflected. So I'll get to your question in a minute, Nick. Let's say you had a, let's do it this way. Let's say you, oh, come on. Let's say we have this current right here. Which way are electrons moving? If the current is pointing that way?
To the right?
It's the opposite way.
The opposite, because yeah, exactly. Negative charges moving left would be the same thing as positive charges moving right. So, which way is the magnetic force on this electron? Help me out. So the X's represent the external magnetic field.
It is upwards.
So let me think. I point my hand this way, I curl it inwards, my thumb points downwards. Because it's negative, I flip it. So there's a magnetic force up. Now, right now, whoops, let me, we expect there's going to be a magnetic force upwards on an electron. Well, wait a minute. If there's a magnetic force up on an electron, some of them are going to pile up here on the top surface. And as a result, there's going to be an absence of electrons in the material down here on the bottom. And literally the top and the bottom surface of this exceedingly thin, Z is like a micron, okay? This dimension is like a micron thick, generally speaking. You'll have this exceedingly thin piece of metal with you'll have an electric field set up. So that would be the electric field. Once you set up an electric field, you could come in here with a DMM, a multimeter, and measure the voltage across here. So you'd use your DMM like a voltmeter. You have just measured the Hall voltage. So if you allow current to run through a very thin piece of metal, you could actually measure a voltage across the top and the bottom with a DMM set to microvolts usually. And that relates to this right here. Again, notice if you know the voltage from your meter and you know the current, you can figure out this stuff. This is a dimension. You can measure the magnetic field with this device. So this device is actually, in a lot of ways, useful for many things. When you do a device like this one, let me get back to it. When you use a piece of metal like this, and you put it and you run a known current through it, right? You could figure out that current somehow and run that through. You could figure out the speed, blah, 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 and you could calibrate this, and this you could use to measure magnetic fields. And so this voltage is very special. It's called the Hall voltage. It's always in every physics textbook somewhere. When this sensor is used to measure magnetic fields, it's called a Hall probe. And so this is a standard device for measuring magnetic fields. If you're ever wondering, how do you measure a magnetic field anyways? You get a Hall probe, stick it in the magnetic field, and it runs a little current through there, and it tests the Hall voltage, and from that, it back computes the B field. So that's kind of neat. And I'm still haven't got to Nick's question, but that's next. Sorry, Nick. I got distracted, and I wanted to hit that one while it was fresh. So just, this is really cool. Velocity selector, Hall probe relates. Great. Now let's take a look at something that relates to Nick's question. And at any time, you can interrupt me and ask questions, okay? Let me see if I can get Nick's first, though. Ah, empty page. Sorry, my bad. Okay, so this is I wanted to get to this figure to answer Nick's question. So let's say we have positive ions here, okay? I hope you agree if you put this as a plus plate, that's a plus plate that's got a hole cut out right there so the ions can snake in. And you make this the negative plate. This right here is called an accelerator. And these are exactly the same as the particle accelerators. And then what you do is stage 2 is a velocity selector. This cleans up the beam in your accelerator. It gets rid of some of the junk that's not going at the right speed. So if you want to do an experiment, what you do is you dial in a different voltage and you are basically dialing in a different speed from your think about this. All of these are going to come in here approximately equal to 0, but because they all start at slightly different speeds, they're all going to come out at slightly different speeds. And the idea is you use this selector to clean up any unwanted velocities. If they're too fast, they go down here. If they're too slow, they go up here. So you get only velocities in a narrow band that can fit through the hole in this plate. All right. And so now let's think. If I have a negative charge on these plates here and a positive charge on these plates here, I'm looking at stage 1. The electric field between the plates points this way. I'll call this E1. Over here, what is E1? Outside of those plates, what's the electric field? Oh no.
0?
0, Gauss's law. What? For firewood? If I do a Gaussian surface like this, isn't the charge enclosed 0? E equals 0, right? So again, I'm looking at electric field 1. I'm not talking about electric field 2. So again, my point is this. This one causes an electric field inside of these plates, and outside of it, it has no effect. Nice. Over here, we could do a different electric field. I don't know which plate's positive or negative, but let's say it's either going to be this way or that way, and you could have a magnetic field as well. And all right. So now let's get to Nick. Make sure, did I answer your question, Nick, how this relates to particle accelerators?
Yeah, that was good. Thank you.
Yeah, stage, they usually have an accelerator stage and a cleanup phase with a velocity selector. Right. All right. Good stuff. All right, so now I just want to walk you through this. In this case, how does this device is called a mass spectrometer. How does it work? You accelerate these ions through here, get them up to speed. You apply a velocity selector to clean up the beam. Now, which way is the magnetic field pointing in this case? Look at stage 3. In stage 3, you enter a region where it's a magnetic field. How can I tell? It's going in a circle, right? That can't be caused by an electric field. It could only be caused by a magnetic. What's the logical orientation for the magnetic field?
Into the page.
Into, let me see. So I point my hands this way. If I curl my hand into the page.
And bro.
Oh, got it. So the field should point out of the page. Agreed, Eston?
Yeah, I'm a lefty, so I keep screwing.
Yeah, I got you. I got you. I mean, you could always use your left, but then I worry about you running into trouble in other classes where they use right-hand rules all the time. You could always do all left-hand all the time and then just know your rules are exactly opposite everybody else. That would work. Okay. We need a magnetic force this way. So the only way to make that work is if I line up my fingers with V this way, curl my fingers out of the page. So that means B external. I already just forgot. What did I say out of? Let me write it down so I don't forget. B external is out of the page. Okay.
I've got a quick question, if you don't
Sure.
mind. So the force at that point, right, of
Yep.
the FB is pointing down where it's drawn. But what happens near impact? Where is the force B pointing?
Let's try this one first. So right here, B is out of the page, right? Everywhere over here, it's out of the page. So just trying to draw it here. So at the point right here that I'm drawing a circle around, what direction is the force at that point? V goes to B.
To the left.
And so take a guess what direction the force is right before impact.
So then it's going up. Yeah.
Exactly. So we see that this does make sense. You'd have a velocity right here, but the force would then be upwards. And that's just the force required to keep it in circular motion, right? So we see that the force magnetic keeps pushing towards the center of the circle. It's center pointing, it's centripetal. All right. Well, let's go backwards now. Let's work backwards. If I know the B field in here is out of the page, what direction is the magnetic force on this charge right in here that I'm circling right here?
It's down?
Yes. So this would have a magnetic force down. So then which plate do we need to have be the positive plate?
The bottom.
Exactly. If I put plus charge here and a minus charge up here, that sets up an electric field up, which sets up a force electric up. And so we see this is pretty similar to what we just worked through. All right. So what I'm going to do here is that's kind of the fun part, the conceptual. Now, at some point, if I could make this just a little bit smaller. Oof. We talked about, I want you to go through this one at home and just kind of work through all this stuff. And you'll see there's a bunch of what if questions down here. So a lot of this is basically just keeping track of the letters, working on the symbols. Notice you have to be very careful because there's two different voltages, right? There's also a, this is a problem with 3 different letter V's, 2 capital, 1 lower. And so there's 2 different plate spacings, and this is a complicated problem in a sense of just keeping organized. It's not that hard mathematically, but you'll see that it uses chapter 24. In a sense, we use chapter 23 for the Gauss's law to know that it's 0 outside. It's using this, yeah, whoa. Cross products. All right, so work on 28.6 at home. Here's the real point. If we work out all of this stuff, I just want to point out, let's do the magnetic force here. So let's just look at the force equation and do one part of this together. Force B, that's Q, V, B, sine theta. But in this case, let's assume sine theta is 90. So obviously there's a sine in here. And I'm going to assume it's 90 degrees because of the cross product. I'm going to assume this goes to 1. Okay. Now this, what should that equal? If there's only one force over here, gravity is negligible on these little ions. What does that magnetic force equal? That's a hint.
The centripetal force? Or
Nice. So it would be M times what?
Oh man, I'd honestly have to look it up. I feel so dumb.
Ah,
V over R?
close. Check the units. Kilograms. He said V over R, right? Kilograms times meters per second divided by meters. Yes. V squared over R. Use those units, people. All right. So now I just want to point out, do you notice that the radius of curvature will depend on, let's clean this up a little. One of the V's drops out And then what do you get? R is equal to, is it mv over qb? Is that right? Yeah, and just pointing out, remember that this velocity, that's a velocity, not a voltage, but it relates to this voltage up here, agreed? Because you know 1/2 mv squared equals E delta V, right? Anyways, okay, so I just want to point out the following. We get the radius, let me clear this out and start over. I know that radius is equal to, whoops, oh, it's on the bottom, my bad. It was M over Q times what, oh shit, I just forgot it. What was it, V over B?
V over B.
Thank you. So now sometimes this is actually written in this way. V over B times the quantity 1 over Q over M. So if you're a physicist, you usually use the bottom method. And we say the radius depends on the charge to mass ratio. Okay? If you're a chemist, you usually use this upper one where you talk about mass to charge ratio. So go figure. Physicists make it a little bit harder than it needs to be, right? Typical. And that's so sloppy, I'm going to erase it and rewrite it.
So in this mass spectrometer, what would we be finding the masses of?
You can't find the masses. What you could find is the charge to mass ratios of different ions. Now think about this.
Okay.
Because you know the speed is the same for all the ions. You know the B field is, that's supposed to be a letter B. That is the worst letter B ever. Let me just get that clearer. You know the B field is the same for everything. So this right here is a constant. This V over B is a constant. Essentially, the radius tells you the charge to mass ratio. So what you could do is, if you have singly ionized helium, that would be helium that has one, say, electron kicked off. And that would be positively ionized, singly ionized helium. Or you could have doubly ionized lithium that would have 2 electrons kicked off, or beryllium, etc. And so the idea is the different elements and different ion concentrations correspond to different peaks. And you can figure out the material composition of a jar of jelly when you shove it into this machine, heat it up, let some electrons or let some ions drift out. When you heat it up, they'll have different ion ratios, and this can give you an idea of how much of different types of material are inside of a sample. Yes. So that is a practical device. I don't know who asked that question, but did that sort of address your... The whole goal is to figure out material compositions, and you're not really getting the mass of any one thing, but you are getting the relative abundance of helium versus lithium versus beryllium versus hydrogen in your sample.
Yeah, that makes sense. I was going to ask, if things aren't charged, how would this work? But
so you could heat them up so they become charged.
That makes more sense.
If you add thermal energy, if you add heat, so a lot of times you could have what's called thermionic emission. So you take a piece, like old school, you could literally take a metal wire and heat it up, and that could boil off electrons, and that would do this, right? Of course, the charge to mass ratio, that you could figure out the mass of the electron relative to its charge. Now, you can't really get Q, you can't really get M, but you can get those ratios. Then if you do this with some other sample, hopefully you could get some of them. And now it starts to get complicated here, right? Because when you apply heat, what percent of them are going to be ionized singly versus doubly? What do you expect for the spectrums? And so you probably do some calibration experiments where you heat up pure lithium, and you know, this is what pure lithium looks like when you heat it up. This is what pure beryllium looks like. And then from that, you can see the peaks. And it gets complicated because some peaks could have the same charge to mass ratio, even though they come from different elements, right? So imagine you kick 2 ions off something that's 8 AMU versus 1 ion off of helium with 4 AMU. Right? Those peaks are going to be the same. So you got to learn multiple different ways to see this. So you need the whole spectrum. That's why it's a mass spectrum. Ha, this isn't even particle physics. Yeah, this is just, this is just lowly chemistry, right? Oh, gotta throw shade when I can, you know. Let's see what I got now. Oh, ouch, ouch. Yeah, I mean, let's face it. The physicists have to do everything for the chemists. Otherwise, they wouldn't get any work done, right? Of course, yeah, I'll shut up now. All right. Oh, the endless fights between chemistry. All right, anyways, so maybe you could skim through this and see. That's kind of a summary. So I'm going to let you work on that more later, and blah, 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 blah. Now, here's something weird. Before I was a teacher, I used to be an X-ray health inspector for the state of Oregon. And I would go around the state and inspect all kinds of weird things. I went into maximum security prisons and looked at their dental units. That was pretty weird. Let's leave it at that. I went into a sausage factory and I inspected their sausage X-ray unit, and they would X-ray meat, and the amount of fat was calculated by how much X-rays were absorbed by the fat. So that's how they tell whether it's 83 or 75 or whatever. And then one of the weird things I had to do, I had to inspect Intel. So I went into Intel and they had these ion implanters. And so here's a variation, here's a practical application of an accelerator. You accelerate some ions, you turn them through this beam, you blast them into a wafer. If you remember, a wafer is just like an 8-inch piece of silicon or 12-inch, depending on what you're doing. And you can literally, well, let's do a short version here. Let me see what the chat was. Yeah, I did some weird stuff. The day I was doing the X-ray unit, this notorious mass murderer was getting his teeth cleaned and they had to kick him out so I could check the X-ray unit. That was a little weird. And it was like, you know, in the dungeon, it was like max security. And then it was in the dungeon underneath that. It was like really weird. So that was strange. Weird day. And then they had all the snipers, right, just following us around in case somebody tried to mess with us. They were just going to shoot them. So it was pretty unusual. Yeah, weird day. And as if this story isn't weird enough, it turns out it was the same. It was evidently Tommy Lee Jones was in some movie where there was a jailbreak scene, and that was the jail. So that's really obscure shit. All right. Anyways, I don't know the name of the movie. I never watched it. I should have. Let me see if I can get this. Let's stay on contact. What were we doing? I just forgot. Oh, yeah. Okay. This is getting it. All right. Sometimes you just got to do some weird stuff. Here is a semiconductor wafer. All right. This is semiconductor physics in a nutshell, like intro to fab. Fab means fabrication. So let's say you want to make a microchip. A typical scale on this might be something like 8 inches or 12. Okay. So it's 8, and this size might be very thin, maybe a millimeter, maybe less, depending what you're doing. And this is silicon. Okay. Okay. So, and you know, there's different size wafers and different thicknesses. So let's not focus too much on the dimensions, but basically it's very large and very thin. That's what you need to know. Now, what you can do is you can take some goo, and this is a liquid, and this is called photoresist. Okay. Photoresist is a chemical a lot like film. When you shine light on it, it reacts. Okay. And so what you could do is then you take this thing and you put it on basically a spinning platform. You put a little piece of what you do. You have a hole here that's attached to vacuum. And when you put this thing on, you turn the vacuum on, it sticks. And then you spin this thing. All right. When you spin it, you guys could probably imagine, I need to draw a pure side view now. Okay. When you spin it, here's a side view of the disk. This is going to spread out, and just like the water spinner from Physics 161, which you all remember, that was so long ago, you get a slightly thicker layer on the outside, but basically a nice thin uniform layer here. Okay, and this thing's spinning really fast, you get a super thin layer of photoresist. Then you come on top of this and you put a pattern. So this is called a mask. Now we're looking at a side view of the mask. So this is side view. The top view of the mask might look like this, where you have a bunch of blocks and maybe some thin lines where people could use wires and stuff. And so the idea is there's certain regions on this mask that will block the light and certain regions which won't. And then what you do is you shine an intense UV light on it, and you get certain regions of this that get affected and certain regions that don't. So you get a pattern built up in the photoresist. Then you pour some chemicals on it, say toluene, and you stick that on there, and it'll dissolve there's positive photoresist and negative photoresist. So some of them, it will dissolve all the parts that weren't exposed. Some of them, it'll erase all the parts that were exposed, whatever. But at some point, then you take the mask away, then you put this in a bell jar or a vacuum chamber, and you take a hot wire, and you put a lot of current through this wire, and it vaporizes. Well, the pieces of metal gradually deposit here, and then you come in and you pour some more chemicals on it, and anything here would not have metal on it. So then what you've done is you've placed patterns, basically metal forms where the photoresist used to be, or if you use the other. And so this is how you can draw wires and things on chips. And so this, you could imagine calculating the resistance needed using rho L over area and this and that. And then the other thing you could do is you could also implant ions into here. And so you could have metal here to make contact. And the idea is you might take ions, either positive or negative. And what you can do is when you take these ions, if you jam them into here, phosphorus and boron are the two common ions for silicon. If you do that, you could create regions in the semiconductor that are better conducting. By implanting these ions, you change the rho. So you could change the conductivity and make this section conduct well and make it connect to this contact so you can blah, 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 blah. How do you do that? This is one step of that process. Oh, where is it? This is the ion implanting portion of that. So this is one step of the fab process. And what you could do is you use this ion implanter, and notice this is a little bit different. They also accelerate it, and that allows the ions to embed deeper. And so this is a very complicated thing. I have a friend that now works up at D-Wave, and D-Wave is making these really complicated three-dimensional circuits. There, he said it blew his mind, and he and I did fab together back in grad school. So it was like, whoa. Anyways, that's just to keep you interested. All right, so you could do that problem at your own and do the math and stuff, but those are some of the practical applications of this. We're finally up to a point where we could start to talk about real life here. And I did have a cup of coffee late in the day, as you can tell. All right, I know that's a tangent a little bit, but I just wanted to keep you excited a little bit. Hopefully that helped. Any questions about any of that? Pretty interesting to me. All right. Oh, go ahead.
Yeah, I just had a quick question. What does the depth like have to do with the wafer?
That's going to relate to the thickness of the channel that's a conductor. It will relate to the resistance of the wires.
Okay.
Right. So rho L over area, the depth, the penetration depth relates to the cross-sectional area of the wire. Sort of, in a weird, you'd have to do calculus, but yeah. Is that good?
Yeah, thank you.
Mm-hmm. All right. In the old school days, I used to work with fluorine, which I don't know if you guys, fluoride will, if you spill like hydrofluoric acid, right? If you spill that on your arm, you won't feel a thing. It'll seep into your bones, dissolve your bones, and kill you. And so there was this weird shower that if anybody spilled it on you, you had to immediately get naked and get in there and just hope you wouldn't die. So yeah, just watch out if you're going to go into fab. It's not a good life. All right. You end up like this. All right. All right. That said, let's get back to some actually useful things. All right. So you could do this problem at home. It's got, if you're interested, that talks about the chip design. You could actually code this up really easily now, right? You've got the starter code that I gave you for a B field. All you'd have to do is add in an electric field, do the two forces, and couldn't you simulate any electric field you want? And this is one in particular, if you're a physics or a CS major, you might try this out. I don't know if you remember the bachristochrome problem from Physics 161. I vaguely recall this shape ends up producing brachistochrons. And so this is a really weird one. If you have an electric field this way and a B field this way, and it starts from rest, think about it. If it starts from rest, what's the initial magnetic force? If it starts from rest, what is the initial magnetic force?
0.
0, because there's a QVB. So there would be no, and the thing would move straight up. So initially, this thing should shoot straight up. As it gets moving, the B field is going to cause a force this way, and it's going to overshoot and get too fast. Then the B field force is going to be stronger than the electric, and it's going to go back down. And so you get these. And now remember, as it slows down, the B field force gets smaller, so the radius of curvature increases, blah, blah, blah. And it gets crazy like this. And so in theory, wouldn't that be fun to see how this propagates? Interesting. Next. Oh, all right. Now we better, that was my fun. Why don't we take our break right here, because this is the logical spot. So I'm going to take a break right now, and then we're going to come back and do a lot of math. All right. A lot of math. And basically we're going to take this to the next level. Charges are moving in wires. We've been talking about the forces on moving charges. More realistic is forces on wires, right? Rather than individual ions flying through the air. So we'll pick up there next, right after the break at say 5:40. Any questions you have, I'll catch those first. Hopefully this is getting cool. Okay, I'll be right back. Any questions before we get back into it? It's hot today. All right. All righty. So let's take a look here on page 144. So hopefully I didn't waste your time with that digression there. If I did, you should tell me in an email or something, but I don't know. I guess that was for me just because I find it exciting. So my apologies if that was a waste of your time. That said, let's try and focus on this one. We're going to learn about this equation where I talk about the force on a wire. It will relate to the external field, and it will also relate to the current. Now, current is not a vector, so but I do want to look at the units of this red piece. So if we looked at the units of this red piece, an amp is a coulomb per second times a meter for the ds, right? Well, if you think about QV, that has the same units, a coulomb times a meter per second. So we see this is a way to make the equivalent relationship between current and force versus charge and force. So charge times velocity has the same units as current times ds. Now, what is ds in this problem? Let me get rid of some of this. In this case, ds is a tiny length of wire, and even though current isn't a vector, we say the direction is the direction of current flow. All right. Now, if we have certain special cases where you have a uniform magnetic field and a straight wire, we actually get this result. So it looks very similar to the last result. And in fact, you know the magnitude is going to have this, the sine theta coming from the cross product. So to be clear, the magnitude of that force, we could just figure out using sine theta, where theta is the angle between them. So let's take a minute and see how this works out in an actual problem. So let's scroll down just a little bit. So, oh, whoops, I can fit it all right there. Okay, so in this case, let's think about this. The B fields are these dots here. So we've got an external B field here. And notice this B field is getting weaker as we get away from the center. This is very typical for permanent magnets. You take two bar magnets and you stick them close to each other like this. The B field could point out of the page, and it would be very strong between the magnets and very weak far from the magnets. So this would be the B field of a horseshoe magnet. It might not be a perfect model, but it is a decent model. Okay, now look at this equation for that B field for a second. Think about this. When x equals 0, the denominator is as large as possible, and you actually get B naught. So B naught is the value of the field at x equals 0. Take a second and verify. You plug in x equals 0, you get L squared over L squared, the L squareds drop out. As x gets big, either positive or negative, whoops, as x goes to the right or to the left, notice the denominator gets bigger and the field gets weaker. So this is a reasonable model for a magnetic field. It's strong in one region, then gets weak after you go away from the magnets. Okay. So now let's try and figure out if this is the magnetic field here and our current is running this way. Okay, there's our current. Let's try and write down the integral associated with that. So again, this is page 144. I'm going to go to the whiteboard. Got a wire here. The current is flowing this way. My B field is large in the middle and smaller out here. The equation for that we said was B naught times L squared over L squared plus X squared. Whoops. In a K hat. So I'm assuming I have a normal coordinate system where this is I hat and this is J hat. Before I get started doing any calculus, please listen right now. Always double check your coordinate system. Double check it. I goes to J goes to K. Remember, the wheel of pain, if we're going to use that to do our cross products, which you will, you have to have I hat goes to J hat goes to K hat. So this makes sense. We have said that the B field is in the K hat. We have drawn it going out of the page. We have confirmed that with our coordinate system. That's all that was. Next. What is next? We're trying to find the force, right? So the force, in this case, is equal to the integral of I ds cross B. And I'll call this B external. More on that later. So that's the field caused by an external magnet. Later on, it gets very confusing because you have the wire itself creates its own magnetic field. But that's a different magnetic field. We're talking about an external magnetic field, meaning a field that is external to the wire caused by some magnets laying around. All right, what's ds in this problem? Help me out.
Dx.
All right, that's on the right track. dx, what else? That's, you see what I'm pointing at there? You know what I'm saying?
Hat.
Yeah, because if we don't have the cross product, we can't do a cross product without that I hat in there. You see what I'm saying? So now we have to do the vectors right. We can't just be cheesy about it and just kind of hope it works out. All right. So that's going to be, how about I just write that in there so I don't run out of space? So this is going to be dx in the I hat. And I'm going to just put that in parentheses here. What's B external going to be? Well, that's that big mess. I'll shove that in. And here we have two things left before we can do this integral, I guess. Well, what's something else that we might need to know if we're going to actually do this integral? Somebody other than Trey. Oh, yeah, the limits. Okay. So I think that was Ryan. Tell me what the limits are, Ryan.
That's a great question.
So let's reread the problem statement to figure out the limits. Everybody else take a look at that too. How long is the wire?
L.
L. So what's the left limit?
Negative L over 2.
Yeah. So in this case, we're going to go from negative L over 2 to positive L over 2. Does that make sense? Are you good with that, Ryan?
Yeah, absolutely. I just don't have the book in front of me right now.
Understood. Understood. Nothing a gallon of vodka can't fix. No, did I say that out loud? Anyways, all right. So in this case, this is what I want you to remember, people, right here. So I know you're tired. It's hot. It's terribly hot. Look at this. Before you do the integral, do the cross product. Remember that. Again, if you want to do this integral, first do the cross product, then do the integral. And more on that soon. Okay, so now I know you can do this, so let's go to the solution and see. Let's see if there's anything else that jumps out at me. At that point, it's like just plug in some crap and do some stuff. That's math, right? Not physics. So let's scroll down there and take a look at it. There we go. So that was the key word. And we see that the limits were the sneaky part. We were told the total length was L. So that's what tells us. So here's what this picture looks like. And so notice you get this ugly integral, which happens to be found probably back here on the back of the book in the integral table somewhere. I see. Yep, it's there. So a lot of the integrals that you see, if you're wondering, like if you don't want to go looking around for tables, just use the table on the back. That gets most of the integrals in this class that have the weird powers and stuff. Okay, so from our integral table, we know this. This is boring, 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 and you get a number. Great. Okay, so if you want to know how to do this, here's the trick. If you want to derive the table, there it is if you're a mathlete. That's great. But so let's look at this result. How could we check that result? Give me 2 ways to check the result.
Unit analysis.
We could check the units. And what's the other thing? Somebody else.
Directions.
Good. So let's check the direction. Now notice, I just want to point out, this one says it's in the negative J hat. Let's see if that seems reasonable, and then we'll check the units. Got it. The units work out. Okay, so I know the units work out because I've seen this a million times. So let's check this one and look for the direction. This claims the final answer is in the negative J hat. Well, let's look. According to our right-hand rules in the book, let me see if I have this somewhere. Sorry. Where's the right-hand rules for this one? Well, you know, point your fingers in the direction of the first vector, curl them to the second vector. The output is your thumb. Again, point your fingers in the direction of the L vector, or the length, curl them to the external field. Thumb should point in the direction of the force. So I point my fingers in the direction of the input vector, the first one, curl them. That doesn't work. That doesn't work. That works. Force is negative J hat. Good. So good job. And then if you check the units, you could look at your standard equation. Rather than checking the units proper, here's a shortcut for checking the units. The idea is you look at an equation you know on the back of the exam equation sheet, maybe something like this one, and you just say, well, I could see this is, I should get amps times meters times Tesla, right? And so rather than try and figure that all out, you're just like, well, I know the original equation. I should end up with amps, meters, Teslas, and we do. So, all right, good to go. So an amp meter Tesla is a Newton. All right, let's take a look. Oh, okay, okay. Let's try to look at one of these ones. Circular loops are very, very common. And you might be wondering, okay, how could I do the force on a circular loop? Well, we need to think a little bit here. So let's draw up, let's just focus on case A for right now, okay? Rather than trying to do everything at once, let's focus on case A. So I'm gonna look at 28.11, case A. I'll just draw this up here. All right. So here is our loop, and I drew the current direction on there. The trick is, this is too hard to do all at once. So what are we going to do? We're immediately going to split it up into 2 single segments, 2 single integrals. So this would be equal to the straight part with current flowing that way, plus the curved part with current flowing that away. So we've got current flowing in this direction here. All right. So I guess if I draw that here, right, we know the current has to be flowing that way in this picture too. Okay. All right. So in this case, this integral we pretty much know already, right? We just did it. So the force on segment 1 should equal the integral of I dx in the I hat. And then we're going to cross that with, now I got to read this problem. I think the B field was external was uniform. Let me read that again. It's uniform with magnitude B external. Current in the loop is I. Okay, watch this, everybody. This is a good point to watch. What we are told the B field is pointing this way. Furthermore, we are assuming this is I hat, this is J hat, which I goes to J goes to K. That must be K hat. What is the external field in this case as a vector? The magnitude is B. What's the direction?
I hat.
I hat. What's the cross product? What's I hat cross I hat?
0.
0. Any vector crossed with itself is 0 because any vector is not perpendicular to itself. Cross products talk about how perpendicular two vectors are. So Chewbacca vector crossed with Chewbacca vector would equal 0. So notice a huge advantage is doing the cross product first. Some integrals you don't even have to do. All right, I did the hard one. Whew, that was rough. Why doesn't somebody else help me with the force on segment 2? I know there's going to be current. I know there's going to be B in the I hat. What is ds?
Is it
When you're going around a circle. dr means a small change in radius. That's not right. That would be going radially outwards. Good. Close.
Is it r d theta?
It's not your d theta, it's r d theta. But that's not quite right, is it? Remember, what do you get when you cross a grape with a mountain climber? Are you crazy? You can't cross a grape with a scalar. Okay, so this is a scalar. That was supposed to be what I was hinting at. Right, Ryan?
Right, yeah. Good
So
old physics 110.
Yes, exactly. So what's the direction? Let me scoot this over a little bit.
The negative r hat.
Not negative r hat. That would be inwards.
Is it theta hat?
Theta hat. So now let's just do a little quick math here. I don't know if you're familiar with circles at all, but at some point we did this. Imagine you're going around a circle here, right? The unit circle. At this point, r hat is this way. Theta hat is tangent to the curve. That's supposed to be tangent. Geez, I can't draw on this weird angle. Ugh. It's like down and... Sorry, let me try again. Okay, so this way would be theta hat. Theta hat is tangent to the circle in the standard math counterclockwise direction. So you probably know r hat is equal to cosine theta in the I hat plus sine theta in the j hat. You know that. Now, if you want, you could figure out this thing by saying, well, shoot, I know that r hat dot r hat equals 1. R hat dot theta hat must be 0 if they're perpendicular. But I also know theta hat dot itself must be 1. And from all that junk, we find out that theta hat is equal to something in the negative I hat plus something in the j hat, right? Right? Think about it. It's going to the left and up. Well, just looking at this picture, if I drew it correct, oh my gosh, it's almost a 45, isn't it? But it suffices to say it's going to have to be sine here and cosine, because this is a theta, this is a 90, this is a 90 minus theta. Again, this is theta, so this is 90. That makes this 90 minus theta. All right. So, so this becomes a sine theta here and a cosine theta there. You don't really need to know that. I write that in the definition of the problem. If you want me to derive that for you, let's do it later. But it suffices to say that this is how you get theta hat. Okay? So up here...
Is this always theta hat?
That's the standard math definition of theta hat, assuming you're using standard math coordinates, which most of the time we would do that. I can't think of a reason you wouldn't. If current flows the other way, you just call it negative theta hat, right? So for math, usually we say counterclockwise is the positive direction for angles. So unless there's a good reason to choose otherwise, we would say this is positive theta hat, that's negative theta hat. All right. You guys are going to laugh when this problem is done, by the way. So I'm going to plug all this in. B is a constant. I can pull that out. And then I get what did I say you always have to do before the integral?
Cross product.
The cross product. If you think, oh, well, shit, this is just some number, I'll factor it out, you're wrong. Theta depends on the angle. So first, plug in what theta hat is, that thing I just wrote down, then do the cross product, then do the integral. So let's plug in this theta hat in here. Oh, geez, I wish I had a big full board. Let's plug this in here. I'm going to pull this out and notice, ribs. One of my favorite problems. Ribs. Okay, whoops. D theta times theta hat, we said was negative sine theta I hat. Okay, which of those terms is going to drop out?
The first.
Yep, I hat cross I hat. So we see again, always do the cross product first. I hat cross I hat drops out. What's J hat cross I hat? Wheel of pain. I goes to J, goes to K. In this case, J goes to I goes to negative K hat, right? I hat cross itself is 0. J hat cross I. So I'm going to write all this down. Holy cow. All right. In this case, what do we get? I'm running out of room. This term drops out. And then I get left with, what was it? Cosine theta negative K hat? D theta. And we see how important it was to do that cross product first. Now the negative K hat will just pop right out. What are my limits? We're doing this part of the integral, right? What are the limits?
Is it negative pi over 2 and then pi over 2?
Good guess. Not right. So remember the standard math definition. We used the standard math definition for theta hat. So now we're kind of doing standard math definition for everything. So that may have been correct for a different problem, but it wasn't correct for this one because I chose the standard theta hat. Does that make sense, Jay? What's the standard math angle for that?
0?
0 to
Pi.
exactly.
Oh,
So
okay.
okay. Interesting. What's the answer?
0.
You could plug in the calculus, but let's see here. When you integrate this, you're going to get a sine function either with a plus or minus, right? And so as you integrate from 0 to pi, let's see what we get here. Let's do the integral. You know what? Let's go to the solution. Just running out of room. Life online. All right, so here we go. All right, so here's it is, blah, 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 blah. Look at that answer. Isn't that fun? Oh my goodness. That's a lot of work for a 0. I'll pause for a second and let you digest. Hopefully that makes some sense. And if you want, what I was about to do is try to draw them. And oh, go ahead, somebody, go for it.
Yeah. It's making sense mathematically, but I'm trying to think about it physically. Like, wouldn't it actually be being pushed up out of the page?
All right, let's think about it, right? So now I need to, so that you got the math on the paper there. I just need to, I got to draw somewhere. So I got to erase this shit. Let's take a look. And if I draw this, we know that this segment of the wire does nothing. Now think, let's do 3 cases. Let's do, there's a current right here. Actually, let's do a couple of cases. Right here, right here, right here. It's the same current. Now in each of these cases, we know the B field for all of this is pointing this way, right? Okay, let's think about this. Start right here. What direction is the force? I goes to B, no. I goes, no. I goes to B. What direction is the force right here? Into. I goes to B, goes to into. So the force is an X. All right. How about right here? I goes to B, goes to into, right? But now keep in mind, some of this field, you could think of this current as being split up into a small piece this way and a small piece that way. The portion perpendicular to the field will produce the field into the page. The portion parallel to the field does nothing, right? It's not going to have a force because the B field is parallel. So here we expect a smaller X. What's the force up at the top?
0.
0. Now tell me what this is, Trey.
That'd be a small dot coming out of the page.
You see where we're going with this?
Yes.
And so it's not that there isn't force on the wire. There's no net force on a loop in a uniform external magnetic field. That's a big deal. Now, wait a minute. Huh. I notice there's a force into the page on this side and a force out of the page on this side. What do you get net on this loop? There's no net force, but there is a, rhymes with fork, torque. My gosh, you're good. If you put an axle right here, you have yourself a DC motor. This is how you make a motor. You put a loop of wire in a B field, you get a twisted, right? You get a torque on it, it spins. Now it's more complicated than that. More on that later this chapter. Isn't that crazy? You get no, so that's pretty cool. So let's check out another one. Let's go back. So that was this particular, now notice that was when the B field was in the plane of the loop. The other one, whoa. Case B, notice the B field is out of the page. So what's your gut tell you in this case? If you had to guess, is there going to be a force? Is there going to be a torque? Is there going to be both? Is there going to be neither? What do you think?
Force.
There's going to be some force on it. What do you think the net force will be? 0, positive, or negative? What direction? Any guesses? Just try it. Or think about it, Al. I'll leave it at that. That way you don't have to respond. I'll get a drink of water. You could set it up the same exact way. Let's take a look at it. In the interest of time, ribs. All right, whatever. Take a look at this one. I'll just pause right here and see if this seems reasonable to you. See if you could read that crazy looking sentence. So in the solutions. This part is just I ds vector, which is equal to I r d theta theta hat. And then I wrote it in Cartesian form because it's a lot easier to do these in Cartesian form. Okay. Notice the B field is different now. The B field is in the K hat. As a result, both terms survive now. So it's trickier. You get these results right here. By the way, if you're clever, you can see a new, it turns out, I don't know if you noticed this, it turns out R hat goes to theta hat goes to K hat. That's the polar form of the wheel of pain. R hat goes to theta hat goes to K hat. So if you're doing spherical or cylindrical polar, that's the new one. Okay, so that's the new wheel of pain, right? I don't know if you see that. There's an R hat in there somewhere, all right? You get a negative J hat times a negative 1, so it's cosine in the I hat plus sine theta in the J hat. That's an R hat. That said, it's usually easier just to stick to Cartesian, people. Look at these integrals that pop up. You're integrating over a half interval of the sine function or the cosine function. Let's go see what you get. You get 2 ribs for the force. Ribs. Okay. Now, look at the straight line segment as well. So I'll pause for a second. You get a lot of these cosine integral type things popping out. So it's looking like we're going to get a force, right? The straight line segment gives you negative 2 ribs. What? No force. now we know this. It turns out this is true. Any closed loop, any orientation of the magnetic field, as long as it's uniform, this doesn't work for non-uniform, not at all, but if you have a uniform magnetic field, the net force is always 0 for any closed loop. Whew, pretty cool.
Really
Yeah.
quick.
Yeah, go for it.
I think I just may have missed it. So when you have, I mean, you have the closed loop, but you broke it into 2 parts.
Right.
Are we adding the 2 parts together? Is that
Exactly. Okay. So the net force would be the force on the upper part plus the lower part. Going back to my whiteboard here.
I think I just missed it when you said
that. So the idea was we take these loops like this and we say it's going to be this plus that. Is that good?
Yeah.
And this represents the first integral and that represents the second integral.
Got it. Thanks.
All right. Yeah, cool. Good question. Now, in this case, let's see what this one would look like. Watch this. Whoops. So let's kind of get a feeling for this. This conceptual stuff can really help with your math sometimes. All right. So in this case, now B external is pointing a different way, right? B external was out of the page. So that's B external. So in this case, if my B field is out of the page and my current's running this way, there's my current. What direction is the force? Downwards, right? So all along this segment of the wire, there's going to be a downwards magnetic force. Okay, that's supposed to be straight down, sorry, because this is B external. Now up here, how about on this segment of the wire? In this case, again, B field is this way. I goes to B, it's this way, right? It's off at some angle. So we see that this one's always going to be pointing like this. Hopefully I did that right. And what we see here is this loop has no net force, but it is under tension. So in this case, the magnetic force would try to make the loop grow in size. Isn't that weird? This would not be very good for causing a DC motor. This would not twist. Do you agree there's no torque here? Think about it. Where would you put an axis to make this thing twist? All the forces are basically radially outwards. You're not going to get a torque. So we see that even though these problems may have seemed worthless at first, we did learn one thing. If you want to make a motor work, you need the magnetic field in the plane of the loop of wire. Otherwise, you don't get any torque. So we see that if the magnetic field is out of the plane, there's no net force and there's no net torque. If the magnetic field is in the plane, there's no net force, but there is a net torque. All right. Questions about that? Let me think here. Let me make up a new fun problem for you. No, I'll do that at the end. I got one. I'll leave it at the end. Let's go back into here and see if there's anything I forgot. Blah, 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 blah. Okay. Okay, we're going to talk about torque in a minute, okay? All right, great. All right, let's see. Here's one you can do at home. See if you can put this all together, and let me see here. You have a rectangular loop of wire. The loop carries some current. It's got this, blah, 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 blah. I think the net force on this loop is? Whoops, I accidentally said it here. It's not 0. Why is it not 0?
Because the B external, the magnetic force isn't constant.
Yeah, exactly. And so just to be just the point of this question was this, to remind you that sure, if the magnetic field external is uniform, then you get this special rule. But most magnetic fields in the real world are non-uniform. So most magnetic fields will cause a force on loops of wire. All right, good job. And I'm going to let you do the math. And this is a good problem to kind of deal with the algebra and lines. So do 28.12 at home. So we have been talking about torque. Let's kind of work out this one right now. And the advantage of using a rectangular loop of wire is this. I don't know if you noticed this. Let me show you a trick before we do this problem to speed our class up a little bit. I just want to show you this. Let's do one segment here, okay? So let's say we have a B field, and let's just say the B field is out of the page for some reason. Who cares, right? And then just to be clear, let's always put our coordinate systems on. Let's say this is I hat. Let's say this is J hat. And this is K hat. Check. Before we go on, does I go to J go to K? I goes to J goes to K. Got it. So let's say there's current flowing this way in the loop. All right. So that's the current. Got it. Now, in this case, let's just assume, let's put this on a grid here, okay, just so we can talk easier. So let's say this is the origin right here, okay? That's the origin. Now, in this case, you could write down the force magnetic is equal to the integral of 0 to some length, because this one starts at 0 and goes to some length of I dx in the I hat cross B external. And that would say, let's say that's B in the K hat, right? Does this sentence make sense? Take a second and think about this. Your B field is out of the page. I'm going to assume it's uniform. And for right now, let's just look at that. This is ds. I'm going with the current, so I'm in the positive I hat. If I was up here, it'd be in the negative I hat. I'm going from 0 to L just because I had to choose some length. Now, what do we always do first? Cross product. So I cross K hat equals
negative J.
Yep. Let's check. Whoops. I'm not even, I can't, you can see I'm going to be safe here. I think Trey's got it, but I forgot what I said already. So what did you say? What did we, it was I cross K. Yep. Negative J. So we're going to get a force in the negative J hat. Good. So now, in this case, usually the current is the same everywhere in the wire. Otherwise, your wire is about to explode. So we're not going to have that happening. So I is a constant, B is a constant, J hat is a constant. Look at this. This would be dumb to do integrals, right? Let's use our shortcut. If B is uniform and you have straight wires, factor that out, right? And isn't this just the 0 to L of dx and then in the negative J hat? It's faster to do it this way. I'll show you, just say it's faster to do it the following way. You could do this and it would work out. You get an L, right? Great. Why not do it like this? If your B field is uniform, so let me write this. There's a shortcut. Skip the integral, and it's just I, L, cross B, which is I, L, B, sine of the angle. The angle is the angle between the current flow and the B field. Well, in this case, what's that angle? 90 degrees, right? So in this case, this goes to 90, and I at least get the magnitude. So there's my force, but something's missing. What's wrong with this?
Direction.
Direction. What's the quick way to get the direction? Negative J hat. Again, I goes to B, goes to direction of force. I goes to B. So it's much faster to do it that way, right? Now, that requires you to practice. But it beats doing calculus all the time, especially on a timed quiz or a stressful final exam where you're like, oh, I only have 2.5 hours. Oh. Okay, so practice this right-hand rule until you're blue in the face. Check every single problem with the right-hand rule. It's so easy to flip a sign, and it's so easy to catch it by doing the right-hand rule to check everything, okay? All right, that said, now let's go back and look at this sucker.
I have a quick question.
Yeah, go for it.
So that force that you just found, is that the force of the bottom line only, or is that
That's
the
correct.
force of the... Okay.
What's the net force?
It's 0.
Right. So what do you think the force is on the top wire where the only difference is current flows the other way?
It's just the opposite sign of it. Yeah.
Which would be positive J hat, but there'd still be this term and this term, but those would be equal and opposite because this one has current flowing up and this one has current flowing down. So once again, we expect net force would be 0, but each individual segment would be non-zero. Is that good?
Oh, okay. That makes sense.
Cool. And again, this was uniform external magnetic field, net force 0. Non-uniform external magnetic field, net force is something. All right. Now let's take a look at this one. K hat's going to be out of the page. I think you know that by now. Let's do part B as a team here. So I'll give you a second to read that question. There's the current. Okay. What's the direction of force experienced by each segment? So let's start with AB. What's the force on segment AB due to the external field?
Is there none? They're the same.
Exactly. Good job. Trick question. When the current or charge, remember, when charges move parallel to B, no force. Well, if current's moving this way, that's electrons moving that way, they're anti-parallel, still no force. Sine of 180 is 0. All right. How about force BC? And I'll just say force BC hat, meaning what is the direction of force BC?
Out of the page?
I got to think here. I think so. So let's call that K hat, right? Do you agree down here force CD is 0? And then hopefully you can see that. So probably this is negative K hat, but let's double check with the right-hand rule. Whoops. Force DA is equal to up this way into the page. So I know Zoom is a little bit weird because, yeah, whatever. It's flipping my image relative to what whatever. You know what I'm saying? This is like the worst way to learn right-hand rules, right? With somebody that's mirrored. It's nothing could be worse than that to learn a right-hand rule. One more way online learning is awesome. Okay, whatever. We got to get it done. Let's get it done. So now I want to get the torque. Can somebody remind me any equation you know for torque? What is an equation for torque?
R cross F.
R cross F. Now that's great. Now I need to go to the whiteboard here because this is going to take forever if I do it that way. Somebody just told me torque equals R cross F. Now notice this is tau, not tau from the last chapter. Don't you love physics? This is no longer a time constant. This is a torque. If we're going to understand this, you need to tell me what R means. Since Ryan was crazy enough to speak up, do you remember what that was, Rye?
In this problem statement?
Just in general.
Oh, just in general. Oh, so that's going to be...
This is a general definition of torque, right?
Yeah, so R is generally from the point that we're interested in to where the force is applied at.
Okay, and I'll just say it's displacement, just to make it sound right. Displacement from pivot or axis to point where force applied. Good. Does everybody remember that? So again, if I had a nut here and I had a wrench, it's not a good wrench, but it's a wrench, right? You know the center of this nut would be the pivot point or this bolt or whatever, okay? And now that would be my pivot or my axis. And then let's say you apply, I'm going to apply a force this way. Let's say that's the force I apply. What's my torque?
0.
How much is
0?
It's nothing. Yeah, so that's not a good way to push on it. What if I push on it mostly up and down, maybe at a slight angle here like this? So let's say this angle is theta, okay, right up here. We don't need the word axis. We're free. Okay, so this would be my applied force from the pivot to the point where the force is applied. That would be my R vector. Now notice you've got a cross product. I just want to point out how fun this is going to be for you. The force has a cross product inside it too, because it's a magnetic force. Have a fun weekend. All right. So yeah, woohoo. Anyways, yeah, but so the idea here is, shouldn't this force be RF sine theta? You know what I'm talking about? Don't you get RF sine theta when you do a cross product?
Yeah.
So of course I'm trying to trick you. It's not RF sine theta in this case. Why not?
It's cosine.
Exactly.
You gave us.
Oh, that Jorstead. We're using this angle, 90 minus theta. Oh, now you know what to watch out for when you're doing torque problems. You have to worry about cross products inside the force. You have to worry about the pivot point. And you need to worry about, do I need to use theta or 90 minus theta, depending on the way things are drawn in your stupid diagram. Did that make sense? So in this case, it's sine of, I'm going to call it angle between. That way, you know, sometimes it's theta, sometimes it's 90 minus. You know what I'm saying? Is this coming back from chapter 12?
Yeah.
All right. All right. Cool. All right. All right. So now, in the interest of time, I think we can get through this if I go to the solutions, and then you can always read it later. But let's go to the solutions here, just so you can kind of, there's a reason to speed through this. Just trust me. Okay. That's the other one, blah, 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 blah. Okay, so there's what we were just talking about. We just worked this out. So notice from the axis to the point where it's applied, that's going to be half the width. So notice I use width over 2 right here. to be clear, this distance right here is half the width. So width, oh my gosh, why is that not drawing? Width over 2. And so if I go this way, it would be width over 2 I hat. And this would be width over 2 negative I hat. And then notice, because the R vector flips and because the force flips, when they flip down here again, both produce a torque in the same direction. So the torques don't cancel, even though the forces do. So scrolling down a little bit so you can see what I mean. If you do it, they both end up in the negative J hat. Now, wait a minute. Negative J hat? What? Is that right? Let's look at it. We better get our coordinate system up here if we're going to understand anything. Here's a loop of wire. Here's an axle right here. And I just told you this way is I hat, this way is J hat, and this way is K hat. And then I told you in the end, the torque direction, torque hat means torque direction. I just said it's negative J hat. After I just told you that the force on this side was, oh crap, I forgot. Hold on. Where is it?
It's positive K hat.
Okay, out of the page on the right. So this is a dot. That's the force. And this is an X. Okay, so we see, what does that negative J hat mean?
It's going to rotate clockwise around J.
Yes, exactly. Grab the axis and align the thumb of your right hand in the torque axis. So this is telling you the axis of torque with your right hand. Negative J hat. Notice this side goes out. That side goes in. Okay. One more time. Grab that negative J hat. This side goes out, the other side goes in. Whoa. So remember that the torque vector specifies the axis of rotation. Oh my gosh, everything's falling apart here. I got a mouse flying over here. What is this? Mouse pad? Oh my gosh. Whatever. All right. Let's go back. I know it's time to go, but I'm going to finish this out so it's in the live stream. So if you have to take off, take off. That said, I'm going to finish it out just because we're so close. There's a really, really exciting result like 10 seconds away. Okay. Look at this cool thing. The area of the loop is right here. HW. Oh, my son HW is digging for oil. But anyways, the area of the loop shows up. And so we'll pick up there next time. It turns out we don't have to do this every time if we learn the next step of the problem. So this will foreshadow. Geez, zoom. I needed this one. So it turns out this foreshadows what we're going to start with next time. And I'll leave it at that. And if you remember, we did this in chapter 3, way back in 110. So we're finally up to magnetic moments and things like that. Yeah, let's leave it at that. You can read this later.